Okay, can you see the screen?
I can see your screen, yes.
Excellent. So let me just introduce myself. I'm Marcelo Lorenzati. I'm not Italian. I'm from Argentina. So I'm an electronic engineer from, I don't know, since quite a long. I'm 48 years old. So for me, when we talk about retro computers, and especially from Commodore, for me, it's not only about the fond memories. It's how about they pave the future for multiple, I would say, professionals and engineers that have been working with this marvelous, I don't know, nice computer. And one thing that is important for me is that the door that opened for the people, as you know, prior to the Commodores, there were no computer for the masses. So, and it's also something really interesting that the Commodore computer were open in their architecture, so you could interface through their ports and investigate and do really cool things that now maybe with devices such as Raspberry Pi is something that we think is usual, but in the 80s that was really something really cool. And also now in the present, it's really nice to be able to be in contact with people, really cool people that know a lot about technology, and it's just a door opener for talking with the great people with a great knowledge. So when I started to work again with this Commodore computer, for me is the opportunity to talk and meet a lot of cool guys and people on the industry. So I hope that continues to be in that way. So now I'm going to be talking about what I have built, which is the pico-rgb2hmi. I know there are other converters in the field that maybe with the same name. So that's why it uses the pico as the initial name. So let's go a little bit on the what is the agenda. So I'm going to be talking about why I did that, a little bit about the architecture that I included there, some of the features that it has, some maybe also some of the future things that I plan to add, a demo, a space for your questions, and any final thoughts that we could have. So as you can see here, this is an application that you can use. I mean, it's really raw application in Python just to prove that you can interface with the board. And let's continue. So as you know, past the initial 80 computers like the Commodore that were using composite or super video images, another standard appeared, not I would say straight hard standard, but it appeared the RGB, which was an evolution of the TV video TV. And as you know, what they did is just to separate the three signals from the originating computer and use separated or maybe composite synchronism in order to be able to place the image into the screen. So one of the things was the limitation on the kilohertz for the swipe, for original swipe, or on the syncing. Usually we're below the 31 kilohertz, which is the limit where you are going to be seeing what is the VGA standard. So the usual was 15 kilohertz. That was what it was used for the NTSC and PAL video formats. You can see a little bit more about the timings on those monitors in that page and in that link that I shared there. And the usual interface that you are going to be seeing for the RGB is the SCART connector, but if you know your computers, your retro computers, you will see that there is no standard regarding the connector itself. There's a plethora of a type of connector. If you have an ST, if you have a Spectrum Plus, or if you have an Amiga computer, is different, the type of the connector, but the signals are, I would say, similar. So this is just a quick view of what I was mentioning. So you have a vertical back port and a vertical front port. That is the time that the system, the rendering, or the computer that is emitting the signal will make a space for preparing the beam. We are talking about the times that we were using CRTs. And you have the horizontal back port and front port. That is the preparation when you have the horizontal sweep with the information from the pixels. And well, basically, this is just a representation. And you can, if you can see on the left, you will see the same that I'm referring on the right, but with signals. The additional thing is that there is no standard regarding the timing. So depending on the computer, you're going to be seeing that the horizontal back port is maybe smaller or higher, and you will need to adjust in your old CRT. Maybe newer monitor will be able to sync or to make the auto alignment of the image. But as I said, there is no standard in the timings. Either if they do overscan, so they use additional lines. Maybe they are stepping in what could be considered the verticals, front and back ports. Some computers draw lines there, so sometimes you need to adjust also the vertical to fit all the information that you are receiving from the computer. So as I said, no strict standard, a lot of variation. And let's continue. What is the problem? So as you know, they are not getting handed, or you're not going to be seeing a lot of CRT monitors that are capable to show this type of images. They are getting old, or they got broken. And some monitors, some professional monitors that you may get, they are really expensive. So the one that we're using in the TV industry. But there are options to connect with a newer screen, the computers. So you have the open source, I don't remember the other, the scan converter. But the problem is really high, the price, basically because the thing with the hardware is that they are using a real powerful FPGA inside of it, and that elevates the cost. But it's a really good choice if you're looking for great image, and most importantly, if you're playing games in these old computers, you want to have real short response times. So if you process images and then you render on the screen, you're going to notice the latency. So that is a problem of the second type of converter, the one you can get from Amazon, so the scarce converter. And the problem is that those converters are just tiny microcomputers with the HDMI head, and they just capture the image, they process it to show it in the resolution that you want. And first problem is that they just destroy the original image. You see artifacts of this of the subsampling or the upsampling that you have there, and also a lot of latency, maybe above the 200 milliseconds, something that is noticeable. And then there are newer options like the Pi0 based rgb2hmi that is really good. The thing that I see on that solution is that they are using a Raspberry Pi Zeros, which tend to be now a little bit expensive and an overkill to have just a full computer just to render another computer. So Also, the complexity of the sandwich of boards that you have. I mean, they call it hats. So they get a little bit complex, and right now the limitation are 12 bits for the resolution. So cost and complexity, and then the other one that are, in my opinion, I don't like to touch the computers just to get it working, and not I don't like it to put things inside. So when you put solutions like the Amiga Digital Video, so you are interfacing directly with the I believe it was a Paula for the video. I always confuse it, but basically you're just reading the video digital output from the 12 bits video, and you are transforming it. So I see it as a little bit invasive, but it's a cool option too. Also expensive because you're using a pi0 and the board that you need there. So those are the options that I saw on that you can have, and I say, why not another one? So as I said, FPGA. This is a really, by the way, a really cool board. It's an open source project for having a development board with an FPGA, which is called iZoom. But as I said, you need to synthesize everything, and you need a lot of memory to host the image. As you know, if the computer that you are capturing the image differs of the sampling rate of the monitor. So if you are using HDMI, the usual is 30 frames per second, 60 or can be 60 hertz refresh rate. So if the image is 50, you need to host all the image to be able to render it into the HDMI. So that means a lot of memory. If you can imagine, by height with the density of the colors that you want to use. And the other problem is the frequency for the capturing, because you're going to be using an SDC converter, and you need to clock that converter in order to capture the image. So imagine it's the usual, if you're using 12 clocks per pixel to capture the information, that's around in the 12 samples per second to have a 6040 by 240 image. That means 144 megahertz. That's not low frequency for a computer, for a microcontroller. So those are the challenges, as I said, with an FPGA. I was thinking, what about using another thing? So there are powerful microcontrollers that you can use in the market with different, I mean, you have microprocessors that host on die an FPGA, so it would be almost the same. But I thought it was a really neat implementations that the Raspberry Pi Foundation did with the RP2040. And besides having a dual core M0 processor, which is not quite outstanding, it's just the basic ARM processor that you can have now on microcontrollers. What I thought that it was really cool is the PIO, the Programmable IO, which is, well, it has two PIOs, this microcontroller, and it can run any kind of program that will interface with the pins, with the IOs of the board. So it was thought as a way to interface any kind of protocol, hardware protocol of a chip that you have. You can code it inside the PIO. The PIO has several state machines that will run its own code, and it will run completely standalone from the main core, from the microprocessor of the board, and it is cycle perfect. So anything that you place on that code, it will loop and it will run perfectly without variations. And the other part that is important is that you can connect it with the DMA just to make fast transfer with the IRQs. So it will transform in a full-fledged peripheral of the board. So if you want, you can build, I don't know, another USB inside the board that has an USB. So that's an idea. So I say, oh, let's try what we can do with this. So this is basically the idea behind of what I built. I say, if we are able to capture the RGB signals and we synchronize with the horizontal and vertical information from syncing, and if we properly configure from the RP2040 the offset and the gain of the image, and so you are going to be able to capture each one of the pixels, like the red, the green, and blue, and you can transport that information in real time, building a program, a really tiny program that is completely outside of the control of the main program, that captures that schema and take it into the video RAM. So that is the first step. You can capture information, you sync with use the horizontal sync to say when you want to start capturing, you have in mind the front port from the image, and you start capturing the pixels and place it into the RAM buffer, and then you prepare for the next one, and so on. Then you count the lines into, you have a full frame of the image using the vertical sync. You can count the lines, you can do all the math, and basically that what is the proposal here. So you can capture all the image and you can render back using another thing. So the cool thing here is that you can either use an implementation for VGA that the Raspberry Pi Foundation did. So if you like VGA, you can use it. There's as part of the examples that the code has, you can implement VGA, but it uses a lot of pins because it does an R2R digital to analog conversion. So I say, why not we can use an HDMI implementation to go to the screen. So I have to add it here. I think I will. It's on another slide, but basically I used an implementation of a guy called Bren 1991, I believe. We did the whole implementation of the DVI protocol, which is the time minimal domain. Well, I don't remember the TMDS. It's not time multiplication. It's the way that the bits are being sent from the chipset into the HDMI. Basically, you have red, green, and blue, and clocking, and each one of that has 10-bit wide for the data that you send, that they are control bits, and it manages the parity because those each one of those lines are differentials. So that's the full idea of HDMI, to reduce the noise and the eye pattern when you transfer information. And basically that's what I did. I just hook that implementation from HDMI and captures the information from a video RAM that I did, and I just whatever I capture from the RGB, I put it on the video RAM, and then another core is rendered on the information back to the HDMI. They use it a lot of micro programs with the PIO, and yeah, and then there are a lot of sublayers of code to manage DMA transmission, interruption, in order to detect when the horizontal syncing happens and start to capture, and well, the application that gives a sense of all the solution. So, no, I also, as I said, it has USB capabilities, and the RP2040 has those capabilities, so you can implement using tiny USB the CDC serial protocol, so you can interface. And as I said, I did a small application to test it. This is just a high-level view of the stack. So you have the DAC PIO, so there's a lot of micro programs to run on the inner layers. Then you have the usage of the peripheral SDK and some libraries to manage the scanning of the RGB, the DVI, video RAM usage, keyboard. I have a parser for the USB command, so you can, if you are fond to use a command line, you can use it from there. And then I am completing, well, I have a video overlay. So you can place on top of your image, you can place information. And now I'm working on a graphical user interface, a signal slot based kind of a graphical user interface, so you can configure it. Right now, I'm not using it in this demo. And well, a new system to do the same things that you can do by commands, you can do it by the GUI. So let's go. As I said, modes from the HDMI from 640 to by 480 up to 1280 to by 720, which is HD kind of images. But the limitation right now is the capture mode. So you have 320 by 240 with 16-bit colors, so limitation memory. And I implemented a 640 by 240 8-bit color mode that well, uses less memory, but you reduce the color density. And it was really interesting how you can use, as I said, 144 megahertz clocking. So you capture RGB colors in 8-bit. Each one, well, it has 24 color depth. So you just shift the bits into a word. You reduce the density that you want in order to do, I don't know, 565 color coding or 332 color coding, and then you shift it back for on a FIFO onto the DMA, and you put it on the RAM buffer. That in real time. So that's the awesome. I never thought that it would work, but it worked. So well, it has some keywords. The overlay that basically I just chop one piece of the rendering, and I just play the image there. Myself, I just tested on these computers, the 128, the Amiga 500, the 1200, and the Atari ST 520. But a group of guys that are helping me with the testing are going to be testing it with the other microcomputers like the Spectrum, or they're using some Macs also. Well, that's the link from the to have an overall view of what I did. And let me just reduce this. Let me know if you can see here. This is my view, and this is, let me show, this is the board. This is the alpha board. Oh, it's not focusing. This is the alpha board. I am waiting for the beta board to come with some improvements on how we interface the image from the microcomputer into the ADC, basically because of the impedance adapting, and also because each one of the computers behaves differently. So I just added a buffer. As you can see, you have there that tiny chip is just it's called AFE, which is an analog front end. It's a small sensor that is used for the cameras, for the CCD cameras, as an example. And you have just a Raspberry Pico, really cheap. So as I said, $4 you can get this chip. This Raspberry Pico is just $4. With board and everything else, is not really expensive. Right now, it's not open. I plan to open the hardware for do it yourself, and then ultimately, in the last part, when I feel confident that the system is working okay, I'm going to open the source code too. That's the idea, the original plan. And as you can see on this screen, this is what is being rendered from the Commodore 124. So just have it here, and let's just run. I had to run or to build. So that's just to show some colors. As you can imagine, if I just reset the computer, you see that it's shifted the image to one side. That is because of the timing of this computer is different with the other, and I just I don't have auto correction of the image. So right now what I have is this tiny, let me just put this on top, these tiny buttons. So the idea here is that I can just move the image from one side to the other. Let me just put this here. So the idea is that you can move it and correct the image right now, but in the future I plan to, where is it? I think I should keep it. And there you go. Okay, as you can see, that's an overlay that I can do on screen. As you saw, it didn't impact in the image, so I can just move it. The problem is the board is completely naked without the housing. So if I touch something, it's not really behaving well, and that's it. So I can, as you can see here, this is doing just an adaptation from RGBI, which is digital levels, into analog levels. So this board can adapt it. And now the plan would be to connect it to the Amiga, which I have there. Let's see what happens. Okay. There it is. So it's connected. And as I said, I adapted the syncing to show this properly. Same thing, you can it's rendering with 8-bit color density. I can change. Let me see. I don't know what else I have here on this computer. Oh, there. So if you know the Amiga tester, you will know that those colors are shifted. That's because of the limitation of the colors. Let's just use F6. Let's see the gradients. So as you can see there are some noises. That's the things regarding the adaptation, but the stability is really good, and well, you can see that with this simple, I don't know, construction, you can have a good screen for the Amiga. One thing that I would like to have that is really complex is to multiplex the audio. I am investigating that, and I think it's going to be a little bit complex. And the other part I want to share is the capability to communicate with by USB. I have to do something which is to enable the USB, because it produces glitches, basically because I need to understand how TinyUSB works. It's a little bit invasive on the timing on the system, so I should have to enable it by pressing the 3 buttons. There you go. And if you pay attention, there might be some glitches on the screen, like some tearing, some lines that you see that gets broken. But now I can connect it here. It should detect the application. Let's see. I think it's not enabled. Let me see. Okay. There you go. Okay, it detected the device. You have some console here. So as I said, you can use it by command line. So now a lot more visible the errors on the screen. Let's just send some commands to move the screen. There you go. So you can do it from here. And let's, I mean, the neat thing is about capture the image. So it will just freeze for a sec and it will process. So Python with USB, with the serial is not really good, but that's why it takes some time. But as you can see, we can capture the image. Let's put something else on the screen. I don't know what else I can show, something more interesting. And if you have question in between and you want to shoot it while I load something else, just go. Let's see. I don't remember what does this dotted has on. Okay, this is the. Let's put another one. This is the gallery. Let's see. Okay, loading. So as I said, right now it's on this stage. When newer microprocessors from the RP20 or no, I don't know which family from Raspberry Pico will appear, that will allow me to introduce more color density, more resolution, and more speed to be able to properly manage the timings. But right now it's in a beta way state. I just choose one game without that it requires a joystick. Let's put another one. No, Lotus Turbo Challenge. I hope I have a sound on this one because it's really nice. And let's wait for something to capture on the screen. Okay. I think that was a reset. Oh, it resetted the board. There you go. Okay. Now, I just forgot to add the joystick. Okay. Any questions? Something that you want to know in between? I just do this.
Let's see if it loads in the background. But thanks a lot, Marcelo. It's really nice. I think we have all tried many options. Like I had one of these card converters, so it was not that good, and it was quite expensive, I must say. I saw as well this Raspberry Pi possibility. There are multiple projects that are documented online, and you can use that with these HUDs. But then also just building it is indeed quite a complex situation. Well, a complex solution for what you want to achieve. But when I see this platform, what you have, let's say, all the package that you have compiled there from that you have built, to me it sounds like it could be used really as a kind of platform to do, I don't know, multiple other things like not only capturing but maybe more video data acquisition or something like that. Will you document all that? Will that be published on your website, or is it already documented somehow?
I created a documentation, yes, of the usage, but as we say, this is the cool thing is that you have like I don't know, 20 bucks or something like that, 30 bucks microcomputer with HDMI and three channels ADC. That's the thing I think is really cool. So you can, I mean, you could do an oscilloscope, a 3-channel oscilloscope. It's around 24 megasamples per sec, the capability of the ADC. So that makes it really powerful for other options that you want to do. And of course, you can extend it. That's the thing. I'm trying to, let me just reset this and to enable narrow capture. I was not pushing it right. Let me see. I think I should drop the application, not really well tested. Okay, yeah, that was the application. Capture, let's wait for something more nice to see on the screen. And there you go.
Yeah.
Okay, and it is processing on the computer, and there you go. So I think it's interesting by you can render from RGB to HDMI, and also you can capture the images, and yeah, that's pretty much what I am building here. It's kind of a fun to do it, and also that the people that is helping me with the testing of the project, I really appreciate that. And my final plan for this is yes to have something open source that is cheap and resolves the problem of having something to connect our retro computers. So that's basically the idea here. Let me see if I just missing something from the deck. Okay, so let me see some final thoughts. So as I said, $40 the Pico, only $4 the ADC. So if there is another member of the family, now it's the RP-2040, which means 2 cores M0 processor and 260 kilobytes RAM. So if another member of the family with more RAMs appear, more density, more resolution. Right now, as I said, we completed the closed alpha. Now we are on the idea is that to have a do-it-yourself hardware beta, then open hardware. It's not a great mystery to reverse engineer a simple board, and then finally open source. That's the idea. So as I said, some of the bugs, the jitter when you enable the USB. Well, you will have aliasing on the borders if the resolution was pure Nyquist problem. If you have something with more resolution on the input and you are capturing with less sampling rate, or it will make make artifacts. And yes, there are some times that the levels of the image will, if there's a burst of noise or something like that, they can shift the gain of the ADC. That's something that we also have on the list of things to cover. That's not something that happens always. And it's simple. That's the thing. It's really simple architecture on the hardware, a lot of work on the firmware side. I mean, that's pretty much it. So I thank you, Sebastian, for the space to talk about this, and looking forward to make it available for everyone else.
Thanks very much. We will be following up that for sure. I don't know if there are any questions. I haven't seen any in the chat, but if anybody has a question, then please ask it now. If not, then I will just stop the recording. And if people have questions coming up, then they can put it in the chat and it can be answered when we start with the next next call. Thanks again, Marcelo.